So, good evening. So, today's class we will start applying the Heisenberg's uncertainty principle, whatever we have discussed yesterday. We will see how the uncertainty in the momentum and displacement becomes more evident if you look at a confinement. Okay, so, we took the example of a free particle in space, solved the Schrodinger's equation and found that still in this case you have a uncertainty which is tending to infinity for locating the particle position in space, but the momentum is nearly precisely described, and therefore, there is a satisfaction of the Heisenberg's uncertainty principle. Now, let us extend this to the case where we confine this electron wave to a small width. Okay. So, sometimes they also refer this kind of a confinement to quantum well, okay, just like you have a physical well where you dig deep and then put something inside, and you cannot expect this object or a person who is inside the well to climb out unless he has sufficient energy to overcome this the potential head of this well. So, similarly, a particle which you put in a potential well or a quantum well should have enough sufficient energy to overcome the potential energy constraint on this particular particle. So, in this case let us say that we have a well something like this, it looks rectangular, and you have a particle inside this well. Okay. So, inside this well the particle is free to move around in one dimensional space, of course. Okay. That means it can move this way or this way. So, there is no constraint on this particle inside the well. So, the potential energy constraint within the well is 0. Okay. Now, outside the well we will put a constraint that the particle cannot escape this well. So, this particle is always trapped. So, this is what we want. We want to make a confinement such that the particle is only within the well and cannot move out. So, therefore, the potential energy outside the well, the potential energy constraint is infinity. That means, the particle should have infinite amount of energy to overcome this barrier and climb across this and then go out, which is not possible. Okay. So, in terms of the wave function, therefore, you cannot have any wave function outside this potential well. Okay. That means, the probability of finding the particle outside the potential well is 0. So, therefore, this becomes the kind of boundary condition for us. So, just at the points, let us say the coordinate system, let us start from this. This is a one dimensional system. So, our x starts from the left end of the potential well, and the total width of this potential well is described by capital D. So, it could be nanometers, it could be microns, it could be millimeters. We have already seen that if your confinement is of the order of millimeters, the energy jump between successive levels is actually very less and cannot be resolved, right, much lower than your value of kBt. Whereas, if the confinement becomes the order of nanometers, this energy jump or the discretization of energy or the quantization of energy becomes more evident, and magnitude wise it is comparable to the energy at room temperature. So, it could be any value d, but let us make a general derivation, and therefore, the boundary conditions that can be written are at x equal to 0 and at x equal to capital D. So, since the potential energy constraint is infinity outside the well, so the wave function will be 0. That means, you cannot find, or there is no probability of finding a particle outside this potential well, it is confined well within the well. Okay. So, therefore, we will be solving this Schrodinger's equation only within the well, right. So, outside the well there is no wave function existing. So, we will solve this within the well with these boundary conditions, and therefore, when we do the separation of variables, okay, we have a function of time, ODE as a function of time, okay, which is an exponential function, the other being a function of space, that is the eigen function problem. And what is this eigen function problem for this case? So, you have minus h bar square by 2 m d square psi, the Laplacian operator in one dimensional space, okay, and your potential energy constraint inside the well is 0, okay. So, therefore, that term drops out and you have E psi. So, this becomes your eigen function problem. So, the eigen value for this is your eigen value, this is your energy, okay. So, once you apply the boundary conditions, you will be therefore able to find out an expression for the eigen value, which is the energy, which is also the expected value of the Hamiltonian, right. So, let us do this. So, I will give you some time. So, in the similar lines that we did the solution for a freestanding particle, now you try to solve this with these boundary conditions. The earlier case, freestanding particle did not have any boundary conditions. So, now the same solution, you apply the boundary conditions, try to find out the constants and the eigen value capital E. Might be easier if you work with the trigonometric functions in this case, okay. So, you can assume that your psi, which is a function of x, is a cos k x plus b sin k x, and what is k here? Square root of 2 h bar square upon h bar. So, yeah, it should be 2 m capital E by h bar square, right, okay. So, now you assume rather than the exponential functions, in this case take this to be trigonometric functions. The boundary conditions may be easier if you apply to the trigonometric functions. The first boundary condition gives you what? A is 0. Okay. So, therefore, your psi now becomes sinusoidal function in space, right, and application of the second condition at x equal to capital D. So, your in this case, so you have k d is equal to n pi and n going from 1 to infinity, okay. 0 again gives a trivial solution. So, therefore, k becomes n pi by d. So, now with this we can actually express the solution for capital E. So, you can substitute for k from, let us say, call this as equation number 1 here. So, into, so let us say this is 1 and the second one is 2. So, substituting 2 into 1, so what do you get for E?
N square pi square h bar square upon 2m.
Okay. So, I am just going to rewrite it like this. You have pi h bar n by capital D the whole square. That okay? So, this is your energy, and now you see the difference compared to okay. Now, if you go back the way we have derived it before for a standing wave, right, before we started the Schrodinger's equation, this was the derivation that we have. Okay. So, we have h bar h square. Now, you convert this to h bar, I think you will get the same similar expression. Okay. So, the earlier case what we have derived was just a standing wave from wave, assuming a wave nature, and we just started from there. We showed the energy of this standing wave will be function of n. Okay. So, for each value of n, so you have different modes of waves and then corresponding values of energy. Now, the same thing through the Schrodinger's wave equation, we can also arrive at the same conclusion that, so the given wave whichever is trapped inside the electron wave or whatever which is trapped inside this quantum well is now quantized, okay, and you have therefore different values of wave functions corresponding to this quantization. So, psi of x will therefore be equal to what? B sin k x. So, where k is nothing but now n pi by. So, this I just use the subscript n to indicate that now the wave function is also quantized for different values of n from 1 to infinity. Okay. So, these are the discrete wave functions or quantized wave functions corresponding to the value n. Okay. And we have also plotted these, how these waves look for n equal to 1, how it looks n equal to 2. Okay. In the standing wave problem we have plotted these. Okay. It is exactly, this is how they are quantized inside the well. Now, the corresponding energy levels are also functions of this discrete levels. So, n equal to 1 will have a particular value of E, n equal to 2 and so on. Okay. So, now the energy levels are also quantized. Okay. So, therefore, now the remaining problem is how do we find out this constant B. Okay. So, how are we going to find this out? So, we will now use the normalization criteria, right. So, we have seen that as per the interpretation of Born, you have psi star psi from minus infinity to infinity. This gives you the probability of locating the particle somewhere in free space. So, in this case now the particle is confined within the quantum well. So, it has to be somewhere from x equal to 0 to capital D. Okay, and you have to locate it somewhere from x equal to 0 to D. So, this should be equal to 1. So, therefore, if you substitute, maybe you can try this. let me see how I have worked it out. So, the value of B should turn out to be imaginary number I by into square root of 1 by 2 times D. So, this is how it turns out. Okay. So, you can just do this as a homework, use the properties of trigonometric functions and check whether you get this value of B. So, the next step is to find out what is the exact location of this electron wave, what is the likelihood of finding this particles and what location can we find it, where we can find it. So, therefore, now we start looking at the expected value of position, which will be 0 to d psi star into x into psi into dx, and if you evaluate this, the solution should come out to be d by 2. Okay. So, this tells you that in this particular case your likelihood of finding the particle is most likely in the center, okay, which makes sense. If you just have a quantum well of width d, more likely it will be at the center. There is no reason why it should go towards x equal to 0 or x equal to d. You have electron waves propagating as left running waves and right running waves, but mostly with the the particle located at the center of this particular quantum well. So, this is with respect to finding the likelihood or expected value of the position. So, similarly we can also do other things, but in this case we will just stop with this exercise. So, this is just to give you in one dimensional confinement how you can use the solution of Schrodinger's wave equation, get the wave function, energy and also the position. So, you could also do the Hamiltonian operation, but finally that will give you the expected value of the Hamiltonian is nothing but energy E, which is already determined as the eigenvalue. Okay. So, you can also apply the same thing for getting the momentum, expected value of momentum as well. Okay. Now, the next thing what we will do is go from 1D to 2D. So, we will talk about particle in a 2D box or quantum well. This is a 2-dimensional quantum well. Okay. So, the previous case was a 1-dimensional well where the particle can only move in the plus x or minus x. Now, this can move along the y as well. So, to just show you, it just looks like our conduction problem where we consider a slab, a rectangular or square slab. So, let us consider a square well now. So, this is your x coordinate and this is your y, and the width in the respective x and y are equal. Okay. your coordinate origin starts from here, and inside the well your potential energy constraint is 0, and at just at the boundaries of the well you have infinite potential energy constraints. So, in this case the particle cannot escape from this 2-dimensional well. Okay. So, just it is similar to what we have done in the 1D. Now, we have to extend this problem to 2 dimensions. Okay. So, the same equation that we have written here has to be written in 2-dimensional space. Okay. And the same separation of variables, this is the starting point, then we have a Laplacian. Now, the Laplacian operator becomes 2-dimensional, and we have to, therefore, we will have another partial differential equation here. We have d square psi by dx square plus d square psi by dy square. So, again that has to be separated into 2 ODEs, one as a function of x, one as a function of y. So, we will introduce another separation of variables there and separate the Laplacian into 2 ODEs, one as a function of x and y, and then we will find the solution in each direction. Okay. So, this is the procedure. First, can you write down the equation in 2 dimensions and then approach this with a separation of variables in x and y space. So, what do you get for the Schrodinger's equation in space by 2m into some connection is gone, or how does it happen? I did not do anything. Okay. So, d square psi by dx square plus d square, this is a partial differential equation, and you also have minus E psi equal to 0. So, now the assumption is we have to again separate. So, we assume that you can separate your psi, which is a function of x and y, as some capital X which is a function of only x and capital Y the function of y. Okay. And now you can substitute this into, let us say, equation number 1 and divide throughout by capital X and capital Y. You have 1 by x d square x by dx square plus 1 by y d square y by dy square plus you have 2 m e by h bar square equal to 0. Okay. So, everybody could get this? Okay. So, now if you again look at this particular, let us call this as equation number 2. So, you see this first term is a function of x, second term is a function of y, okay, and what is this? Constant. Okay. So, therefore, each term has to be equal to a constant, right. So, therefore, we can say 1 by x d square x by dx square has to be equal to another constant, we will say this is k x square. Okay. So, now we should also put a minus sign here, we will see that y in a brief time. So, you have also similarly 1 by y d square y by dy square should be another constant. I am just distinguishing this constant from this constant by using the subscript x and y. So, you have a different constant in the x direction from the y direction. You can also use L and m as two separate constants here. And why we put a minus sign here? Because the energy value should always be, magnitude should be positive. Okay. So, if you therefore take, so if you equate this to the energy, so you have 2 m e by h bar square will turn out to be k x square plus k y square. Okay. If you do not have this negative sign here, so they can become negative and this tells you non physical values of energies. So, which is not possible, and therefore, so these constants have to be here explicitly negative, and that is why we say minus k x square. Okay. If k x turns out to be negative, again this will become positive. So, in order to make this explicitly negative, we depict this as minus k x square and minus k y square. Okay. So, now these are like two ODEs for which you can find out the solution individually for so please solve three and 4. I think trigonometric functions is better. Yeah. Yeah. So, what do you have? It is similar to the earlier case in the one dimensional space. So, x of x will be again, yeah, let us say a cos k x of x plus b sin k x of x. Similarly, y of y, let us say something like c cos k y of y plus d sin k y of y. Okay. So, I think you can use the boundary conditions which we have proposed earlier for 1D, we can do the same thing now in 2D space. So, your psi value, for example, at x is equal to 0, for example, and for any given value of y, right. So, that is at the left boundary. So, this should be equal to 0 because the potential energy constraint is infinity. So, then what will happen to the corresponding value of x at x equal to 0? So, this is equal to x at x equal to 0 times y of y, right. Okay. So, this should be equal to 0. So, y of y, if it is 0, the entire solution is trivial. So, therefore, we have to explicitly say that x of x equal to 0 is equal to 0, okay, and that becomes the condition to one of the boundary conditions to solve this. So, you have for this particular solution boundary condition is x at x equal to 0 is equal to 0, and similarly you have x at x equal to d also should be 0, and similarly for the y problem. So, all these boundary conditions are linear, and hence I mean whenever we use separation of variables, the respective directions also will get the same boundary conditions. Okay. So, therefore, if you apply the boundary conditions, okay, so what do you see, that directly this term gets out, this term also goes out, you have only sign functions in x and y. And what about the corresponding eigenvalues? So, we will have the condition that k x d is equal to, let us say n pi, okay, n is equal to 1 to infinity. Similarly, we will have k y d will be, let us use m L here, okay, L pi along the y direction. So, where L is also from 1 to infinity. So, therefore, finally, how do we determine E? So, 2 m E by h bar square is equal to k x square plus k y square. So, you can now substitute for k x as n pi by d and k y as L pi by d, and therefore, what do you have for E? Is that okay?
Yes, sir.
So, similarly, what about the wave function psi? So, we will have the product of x and y, which gives you the wave function in space, right, because we have assumed for separation of variables that psi is equal to x of x into y of y. So, the resulting solution, therefore, now since we knocked off the cost terms, we have only the sign terms. So, b times d is another constant. Okay. So, therefore, we can just write this as one global constant, we will call this as c, which is a function of ln, and we have sine. What do we have? So, we can have n pi x by d and the other sign which is a function of L pi y by d. This is the corresponding expression for the wave function, and this is the corresponding expression for the energy possessed by the waves. Now, we know that in all these cases your L will go from 1 to infinity, similarly n also will go from 1 to infinity. So, now if you look at, for example, compare this to the 1D case. So, what do you have? So, you have an additional quantization due to the second dimension. So, earlier 1D case you had only quantization in the x direction, which gave to one particular mode. Okay. So, L square pi square h square by 2 m d square. Now, on top of that you also have a secondary confinement or quantization in the y direction, which gives rise to this in the y direction as well, which is n square. Okay. So, now if you substitute these values, say L equal to 1 and n equal to 1. Okay. So, the values of energy irrespective of whether L equal to 1 or n equal to 1 or L equal to 2 n equal to 1 or n equal to 2 L equal to 1, whether you flip the values of L and n, the values of energy is going to be the same, whereas the values of wave functions are going to be different, right. So, in one case you have function of x, the other case you have function of y. So, when you say for example, L equal to 1 and n equal to 2 in one case, and the other case you have n equal to 1 and L equal to 2. So, in terms of energy this is not going to make any difference, right, whereas in terms of wave function this will make a difference because your n is associated with x and L is associated with y. So, this is called degeneracy. Okay. So, this term we will bring in now, or people refer this to as degenerate energy states, or energy levels. Okay. This is a very common term in quantum mechanics, people talk about degeneracy. So, what is degeneracy? So, degeneracy is nothing but you have different modes of waves, okay, but the same value of energy. So, they will have different wave functions, but the same possessing the same value of energy. So, if you look at the energy state, they will be occupying the same energy level, but they are two different wave functions. Okay. So, in terms of just only looking at the energy levels, it looks like they are degenerate, that means they occupy the same energy level, whereas while from the wave function point of view they are two distinct wave functions. So, this is a very common thing that happens especially in two dimensional confinements. In one dimensional confinement you have no degeneracy, each particular wave function occupies a given energy level, whereas in two dimensions you can have more than one wave function which is occupying a given energy level. In 3 dimensions you can have more, you have more degenerate states in 3 dimensions. Okay. So, therefore, this is a very, so you see how we have progressed, starting from 1D we have a freestanding wave where there is no confinement, there is no discrete waves, it is all continuous, and now then we put a confinement, then we see that there is a principle called quantization happening, you have discrete energy levels, you have discrete wave functions, and again the 1D confinement is different from 2D. In the case of 2D now you have secondary confinement happening in this y direction, and because of this we have introduced this concept called degeneracy. Okay. So, this is a very important concept, we do not have to now go to 3D, because in 3D you will just expand this to a third dimension, you will have another k square, and similarly you will have another sine function there, but nevertheless you will have additional degenerate states. Okay. So, now how this degeneracy for example applies to electrons. So, electrons are somewhat special because they have to obey what is called as Pauli's exclusion principle. So, what happens is if you apply only the Schrodinger's equation for the one dimensional quantum well, it tells you that each electron with a given wave function will occupy a particular energy level, but however that is not the complete picture. So, you have to also apply the Pauli's exclusion principle, which states that you have an electron with a spin which is plus half and spin of minus half, okay, and these two are two different electrons. Okay. So, therefore, there is a degeneracy already coming in because of the application of Pauli's exclusion principle. They may occupy the same energy level, but they are two distinct not wave functions, because the Schrodinger's equation cannot predict it unless you apply the Pauli's exclusion principle, and you have to put this as an additional constraint. Okay. So, this is something that you have to remember. Okay. I am not going to go into lot of details why the Pauli's exclusion principle came about and all that, but you should just apply this as an additional constraint when you deal with electrons. Okay. So, therefore, so far whatever energies that we have dealt with, they were all your translational kinetic energies, right. So, they were all dealing with particle motion either in one dimensional space or two dimensional space. So, when we started this, we looked at the contribution of different energies to the microscopic energies. So, just to give a review, we will go back to that. So, that is the same order that we are following here as well. Yeah. So, we talked about the different energy contributions in micro scale, and then of course, we had classified this into classical particle picture, the other is a wave picture. Particle picture is classical Newtonian mechanics, which already you know what are the contributions to translational energy, rotational and vibrational. Now, we are trying to do the same with using the Schrodinger's equation in the quantum level. So, we have now already at that time I stated that the translational energy is given by h bar k square by 2 m, and now we have derived this particular expression and stated what is kx, ky, kz. If you have 3 dimensions, you have confinement in all the 3. So, therefore, the translational energy is already been derived. Now, the next step is to look at the other 2 energies, one is the vibrational energy and the other is the rotational energy. So, with the purview of Schrodinger's wave equation, how do we consider these 2 now? Okay. So, I will give you an overview of first looking at vibrational energy, and then we will go to the rotational energy, is a little bit more complex. Okay. So, we will look at the derivation of quantum vibrational energy. I will give an introduction and stop, we will not have enough time. So, in the case of quantum vibrational energy, how do we, what kind of a model do we apply? In the case of macro scale, we applied a spring mass system, okay, and then we said that the overall energy is equal to the vibrational energy. The vibrational energy is nothing but both the kinetic and potential energies together. Okay. We are going to do something similar, but using the Schrodinger's equation. So, we will use the harmonic potential model, and this was also described in the very beginning under the introduction, if you remember. So, I talked about the interatomic potential. Okay. This is molecular dynamics calls it as Lennard-Jones potential. So, when the 2 atoms are sufficiently close, you have repulsion force, too far away, then they have attraction force, and therefore, if you plot this kind of a potential diagram, so you have the energies, interaction energy plotted on the y axis, you have plus and minus, and you have the distance. Okay, if they are too close, you have repulsion force. So, this is your repulsion potential here, and then they are separated, then you have attraction potential, and then this goes exponentially. So, this is your attraction potential, and if you are just taking it away and away, the attraction potential goes to 0 asymptotically. Okay. So, how do we take into account? So, this is your actual potential constraint that you have to put in the Schrodinger's equation, but however, you see this is a very complex potential, right. So, you have a power law dependence, and that is different for the repulsion, different for the attraction. So, in order to make it simple, we use the harmonic potential model, which makes an approximation that you have a parabolic variation of this potential with x, So, that means you can say about some position x naught, this is your equilibrium separation between the atoms. Okay. So, less than that there is going to be repulsion, more than this it is going to be an attraction. A very simple model which describes this in a parabolic fashion, and if you plot this harmonic potential on top of the actual potential, this will how it will look. So, this is your harmonic, just a parabola about the mean or equilibrium position x naught. So, this is your harmonic potential. So, since we are not looking at numerical simulations, but a simple analytical solution, we always represent this interatomic potential by means of this harmonic model, and therefore, in the case of harmonic model, what will be the potential energy constraint? Half of k times x square. So, this is just like in your macro scale spring mass system, this is your potential energy associated with the spring mass system. Similarly, we assume that, so here you can replace this as, if you want, x minus x naught the whole square. Okay. So, about the equilibrium, if your x is less than x naught, okay, so you have a potential like this, and if your x is greater than x naught, you have potential symmetric about x naught. Okay. So, now we make a harmonic model assumption, we also assume this kind of potential will work well, parabolic potential, we will just substitute this into the Schrodinger's equation. But now the Schrodinger's equation will become difficult to solve, because now we will have an additional term which will be function of x, and therefore, the coefficients will become non constant, but a function of x. Okay. So, then this has to be the resulting, we can still use the separation of variables, but the resulting ODE has to be numerically solved. Okay. And then in the next class I will give the procedure and I will give you the solution also. Alright, and then we will see how the energy levels look for this problem, and then we will go to the rotation problem. Alright.